Hi everyone, I'm Yue from University of Pennsylvania. Today I'm going to present our recent work on cloud IPG virtualization, which is advised by Professor Li. In the past several years, IPG have been deployed into several clouds to support on-demand acceleration. However, the system support for IPG in the cloud environment is insufficient. At first, the resources management strategy used in existing cloud is simple. In the existing clouds, one IPJ is exhaustively allocated to one application, regardless of the amount of resources used by these applications. But we have observed that diverse applications use distinct amount of resources. Thus, this simple resources management strategy could lead to a low resources utilization. Moreover, the commercial IPJ compilation tool can only map one application onto a single IPJ device. Thus, if users want to improve the performance by using multiple IPJs, they need to manually partition the application and carefully handle the inter-IPJ communication, which leads to a high programming complexity for the scale-out acceleration. The root cause for this limitation is that IPJ are not virtualized. Virtualization is the foundation of cloud computing. Then how to virtualize IPJ in the context of cloud environment? This is a challenging task since IPJ are radically different from traditional computing devices. At first, CPU application describe a sequence of instructions that are executed in the temporal domain, while IPJ application describe physical circuits that are directly mapped onto the spatial architecture. Moreover, IPJ has a long compilation time, and perform IPJ compilation at the runtime could lead to a high overhead. Finally, a more important difference is that the CPU application can be executed at any time point without changing the execution result, while IPJ application cannot be relocated into an arbitrary location without causing correctness issue. Due to these differences, the virtualization technique developed for traditional CPU-GPU devices cannot be trivially applied for IPJs. In the presentation, I will first briefly review the work on IPJ virtualization. Then I will present our solution ViTAL and the evaluation results. Looking back into the history, the early work in the broad context of IPJ virtualization dates back to 20 years ago, even before cloud computing became available. The representative work is a score which proposes a compute model that links computation nodes and memory blocks by streams. More recently, slot-based methods have been proposed by partitioning physical IPJ into regions, and all regions provide the same amount of IPJ resources and the same interface to the peripheral devices. These regions are then abstracted as a pool of virtual IPJs. User applications are offline compiled onto these virtual IPJs and are deployed onto physical IPJ at the runtime. Since the resources are managed at sub-IPJ granularity, this method enables IPJ sharing and improve the resources utilization. To reduce the managed complexity, this method typically partitions physical IPJs into regions with the same capacity. This makes it hard to support diverse applications, and the improvement in resources utilization could be limited due to the internal fragmentation issue. Moreover, this method neither provides support for scale-out acceleration. MorphOS is another interesting work on IPJ virtualization that achieves much better IPJ sharing than the slot-based method. It provides two operating modes and switches between these two modes based on the load and the resources availability. The low latency mode uses the slot-based method, while the high throughput mode compiles a combined application onto a single IPJ to enable IPJ sharing. Here gives an example to illustrate the high throughput mode. This mode can achieve better IPJ sharing than the slot-based method, but the improvement could be limited due to as it has no multi-IPJ support. Moreover, since performing IPJ compilation at runtime could lead to a high overhead, This method needed to offline compile many combinations to support the diverse runtime resources allocation, which increases the offline compilation cost. With no multi-IPJ support, this method also requires users to partition large applications to realize scale-out acceleration. This is a summary of this method, and our goal is to provide a solution to efficiently virtualize cloud IPJs. In this work, we target a platform that IPJs are connected with each other through the data center network. This is similar to the configuration used in Microsoft IPJ Cloud. We then provide a virtualization solution for the homogeneous IPJ cluster. ViTAL virtualized the IPJ cluster into a single and large virtual IPJ, so user can develop applications without considering the capacity of the physical IPJ. Then a compilation framework is developed to partition the user application into virtual blocks. The number of virtual blocks is automatically determined by based on the amount of resources used by the application. At runtime, these virtual blocks are deployed onto physical IPJs. One feature of ViTAL is that the virtual blocks can be relocated into different spatial locations without recompilation. So we can reuse the compilation results to support different resources allocation, leading to a low compilation cost. The relocation capability also enables IPJ sharing to improve the resources utilization. To support scale-out acceleration, ViTAL provides a latency-insensitive interface for the inter-block communication. Application can be partitioned at the boundary of virtual blocks and then deployed onto multiple IPJ to support different resources allocation. ViTAL contains 4 layers to realize these functionalities: the programming layer, system layer, compilation layer, and the architecture layer. The architecture layer is the core of ViTAL framework, which provides the abstraction and IPJ implementation. We abstract IPJ into an array of identical virtual blocks. Each block provides the same amount of on-chip resources and the same interface to the peripheral circuits. A latency-insensitive interface is provided for the inter-block communication. This interface contains FIFOs for data buffering and a control logic to manage buffers. This control logic sends clock-enabled signal to the user logic in the virtual block to control its execution based on FIFO status. Specifically, it clock gates the user logic to halt the execution when the input FIFO is empty or the output FIFO is full. This communication mechanism can effectively hide the communication latency. Thus, the interconnection can be either implemented by the on-chip interconnection or off-chip interconnection without changing the design of the user logic. The interface is automatically generated by our compilation framework without increasing the programmer's burden. To support this abstraction, we partition one physical IPJ into 3 regions. At first, we create identical physical blocks to implement the virtual blocks. We then create a communication region to implement the latency-insensitive interface, and the service region, which contains the essential circuits to virtualize the peripheral devices. Here is an example to show the virtualization of onboard DRAM, where the physical blocks use virtual memory address to access the DRAM to ensure a secure execution environment. At runtime, one physical block is allocated to implement one virtual block. All physical blocks are identical as they provide the same amount of resources and have the same spatial resources constraint. This allows us to reuse the compilation results without recompilation. To create identical physical blocks on the commercial IPJ, we leverage the fact that IPJ have a column-based architecture. So we partition IPJs at the row direction to create identical physical blocks. But we also know that this column-based architecture is only a simplified view of IPJ architecture. and the commercial FPGA introduced several other heterogeneities. These heterogeneities have been handled in our FPGA implementation, and more details can be found in our paper. A certain amount of FPGA on-chip resources need to be reserved to implement the latency-insensitive interface. So we need to minimize this resources usage to maximize the amount of resources that are available to use applications. We first consider the virtual to physical mapping. If we allow a flexible virtual to physical mapping, then a complex interconnection network is required to connect every pile of physical blocks. To simplify this interconnection network, we first optimize the spatial order of virtual blocks. So most interblock connection are between adjacent virtual blocks. We then preserve this locality information during virtual to physical mapping. So the network only needs to connect adjacent physical blocks to simplify the interconnection network. For the interconnection between non-adjacent virtual blocks, we will create a bypass interconnection net, which is combined with user logic and mapped into the corresponding physical block. The interconnection between non-adjacent physical blocks is then realized by a combination of the interblock network and the bypass interconnection net. We also notice that communication latency of two adjacent physical blocks will be deterministic if these two blocks are mapped onto the same physical FPGA. Then we can remove the FIFOs to further reduce the resources usage of the interconnection network. Here we give a conceptual example to show how the interface works without FIFO. When a physical block outputs a data token, the corresponding control logic will notify the adjacent control logic, which then calculates the arrival time of this data token based on the communication latency of the on-chip interconnection network. And we will let the user logic start execution when the token arrives. But note that we still keep the FIFOs for the inter-FPGA communication, since the off-chip interconnection could have a non-deterministic latency. We then develop a complete compilation framework to map application onto the proposed abstraction. This compilation framework reuses existing high-level synthesis tool to convert application into Verilog RTL code. We then reuse the front end of existing FPGA compilation tool to synthesize the Verilog code into netlist. A custom tool is then developed to partition this netlist into multiple virtual blocks. This step is developed to minimize the number of interblock connection and to reduce the requirement on communication bandwidth and ensure that the partitioned netlist can fit into the virtual block. We then develop another custom tool to generate the latency-insensitive interface based on the user logic in the virtual block. This step will develop two versions of latency-sensitive interface for each pair of adjacent virtual block. One version contains FIFO and is used for inter-FPGA communication, while the other one has no FIFO and is used for intra-FPGA communication. We then reuse the backend of the existing FPGA compilation tool to map virtual blocks into the physical block and map the interface into the communication region. APIs from RapidWrite are reused to relocate the mapped virtual block into other physical blocks. Finally, all these individually compiled components are integrated into monolithic designs by the backend of the commercial FPGA tool to generate the final bit streams. The last step generates multiple bit streams to support different resources allocations. For the system layer, we first add a system controller to manage the FPGA cluster. It provides APIs to hypervisor for a simple system integration. When user requests to deploy applications onto FPGAs, the system controller first searches the resources database to find the available physical blocks, then searches the bitstream database to find the appropriate compilation result. we know that the limited inter-FPGA communication bandwidth could become a performance bottleneck in such a system. So we provide a communication-aware resources allocation policy. With this scheduling policy, the system controller tries to allocate a single FPGA for the application. If it cannot find such allocation, then it tries to partition the application at the virtual block boundary that has the minimum requirement on the communication bandwidth to minimize the pressure on the interconnection network. We evaluate the ViTAL framework on a custom-built FPGA cluster, which contains 4 FPGAs. These FPGAs are connected through a bidirectional ring network, similar to the configuration used in the AWS cloud. We include 2 baselines in the performance comparison. In the first baseline, FPGA resources are not virtualized and are managed at per-device granularity. We choose this baseline because it is widely used in existing FPGA clouds. Another baseline is the high throughput mode of AmorphOS. We choose this because it can outperform the slot-based methods. 3 benchmark sets are used in the evaluation. The first set contains several small synthetic benchmarks to evaluate the architecture layer. The second benchmark set contains several machine learning benchmarks to evaluate the compilation layer. In this benchmark set, each benchmark has 3 accelerator designs to account for the diverse demands on cost and performance in the cloud environment. The third set contains several large workload sets to evaluate the system layer. Since no real-world workload set using FPGA is available, we synthetically generate these workload sets. This is the implementation of the abstraction on the commercial FPGA, which contains 10 physical blocks. The amount of resources provided by each physical block and the communication bandwidth provided by the latency-insensitive interface are presented. We also observe that the optimization on the latency-insensitive interface effectively reduces resource usage by more than 80% and is controlled below 10% of the total FPGA resources. The evaluation also confirms that the additional partition step only incurs a marginal compilation overhead, since these additional steps have a much lower runtime complexity than the place and route step. For the system layer, we use the average response time as the performance metric, which includes the wait time and the execution time. Compiled with the non-virtualized baseline, ViTAL achieves 82% improvement due to the efficient FPGA sharing. While comparing with AmorphOS, ViTAL also improves the response time by 25%. This is because the high throughput mode of AmorphOS does not provide multi-FPGA support. So in some cases, the combined application is too large to fit into one FPGA. The system performance of AmorphOS is not improved over the non-virtualized baseline. This presentation briefly describes our virtualization solution for cloud FPGAs. More details on ViTAL can be found in our recent paper published in this year's PLOS. Thank you for listening, and I would be happy to answer questions.
Okay, thank you for that great presentation. Let's see if there are any questions in the chat. Okay, so while people are thinking about questions, have you sort of thought about how you might change the FPGA architecture to better support virtualization? So instead of creating these layers on top of the FPGA, what sort of features might you want to bake into the FPGA in the future that might make these sort of features easily available?
Yes, this is a good question. So we have think about this. I think here one thing is sorry, I think I need to change it a bit. So I think one thing here, while I partition the physical block, the capacity of the physical block is constrained by the partial reconfiguration feature provided by the commercial FPGA. It limits my it set a minimum boundary of the capacity. So I can only have 10 physical blocks in the commercial FPGA. So one thing I think in the commercial FPGA, if I want to change, I think it can reduce. It is better if it can reduce the partial reconfiguration granularity. So I can create a more fine-grained physical block to improve the resources utilization. Another thing is should be the communication, the latency insensitive interface. So now I need to have an entire region to implement the communication interface. Is the region 2 in the figure, but the latency insensitive the logic of the latency insensitive interface is very small and cannot fully utilize this region. But I must have this region due to the constraint from partial reconfiguration. So it will be better as the same. It is same thing. It will be better the partial reconfiguration feature can be more flexible. I think this is one major feature I want to have if the commercial FPGA can support.
All right, great. Thank you. That was a very good, insightful answer. We have one question in the chat. Have you thought about the security aspects of sharing the FPGA? What about privacy of applications that might use the same FPGA?
It is the security. It is about the security issue.
Security and privacy of possibly multiple different, customer designs sharing the same FPGA.
Yeah, so we have two things to guarantee the privacy or security issue. One thing is that we provide the virtualization support for the peripheral devices like the onboard DRAM to ensure a secure execution environment. So users use a virtual address to access the onboard DRAM. And another thing is during virtual to physical mapping, we only map one virtual block into one physical block. So the physical blocks are not shared among users. So there is no resources. So the virtual blocks are not shared among users to ensure the security. I think we provide these two features for the security.
Okay, any other questions? Please feel free to post on the chat.
I'm gonna chime in by voice because I can't type easily on my phone. I was just wondering about the fragmentation issue when you create and destroy accelerators. This is still gonna create some internal fragmentation, isn't it?
Yes, because the capacity of the physical block is quite large, so still has some internal fragmentation issue.
Sorry, I think I actually meant internal in the FPGA, but external between your physical blocks. So do you envision having relocation on the fly? Is that possible? So when you want to free up some space to make a bigger region available, for example?
Oh, it depends on the application can be interruptible or not. So some, like in the current cloud FPGA, like in AWS, the application on-demand service, it cannot be interrupted in the middle of the run when it is running. So I think the system can provide this feature to relocate application on the fly, but it depends on whether this application can be interrupted or not. So it's like if it interrupts, some application may lose the computation result and the user may not want this happen, then I cannot relocate that on the fly. But the system provides this feature, can provide this feature.
So yeah, I understand the application needs to be able to support it because it has state.
But yeah, so if
your system right now doesn't provide that feature. It's something that it could do in the future. Oh, it does provide relocation. Yeah. Oh, you just start over essentially.
Yeah, it's a provided feature, but it relies on the application.
All right, any other questions? Okay, if not, then let's thank the speaker, and I will see you next week. Thank you all.
Thank you.
And thanks for the
Yeah,
great presentation again.
Yeah, very interesting work. Thank you.